Welcome again, guys. So we're gonna continue now with examples on the analysis and design of synchronous sequential circuits. So let's try our first example here, which is basically analysis example. So we are given a circuit, a digital circuit, asynchronous digital circuits, and here are some requirements or some problems, that we're gonna solve. First, we need to know the type of the circuit, either Moore or Mealy. We need to find the equations for the flip-flop inputs. We have here two flip-flops. Both are D flip-flops, okay? So we want to know the input equation for the first flip-flop, which I call D flip-flop A, and the input equation for the second flip-flop, which I call D flip-flop B, okay? And of course, the output equation. So we have here two outputs. One is called YA, the other is called YB. Okay, we need to find the state table and the state diagram. Okay, so 4 requirements, 4 questions. This is basically the analysis steps, as we said. Okay, so let's try to do that. So let's now write something in here. So the first question is if this a Mealy or Moore circuit. So we know that for a Mealy circuit, the outputs, I mean YA and YB, for Mealy circuits should be a function of the outputs of the flip-flop QA and the QB, and also the input X. But is this the case here? No, because basically, look, YA is just shorted to QA. I mean, YA is exactly equal to QA. It's a function of QA only. And YB again is shorted to QB. It's again function of, or it's equal to QB. I mean, function of QB only. So Y is not function of X, the input of the synchronous circuit. So that's basically a Moore. It's not a Mealy circuit. So what else? So it's a Moore circuit. So this is basically a Moore circuit. Okay. So that's let's check this. Yes, it's Moore. So for any step, we're gonna solve it first using the pen. Then we're gonna show the correct answer. So a second question is the equations. We have here, we should figure out 4 equations. dA equation, dB equation, YA, which we just figured out right now, and YB. So let's start by the easy one. So YA is basically QA. They are just shorted. Whatever on QA, it will be YA. Whatever the state of the D flip-flop A, this is basically YA. If the state is 0, state means the value of the Q. If the state is 0, YA will be 0. If the state of A is 1, YA will be 1. And same as QB and YB. And YB is equal to QB. Now DA and DB, they are really easy as well. So DA, for example, is the output of this XOR gate. So basically this XOR takes an input as QA. One may say why we didn't write YA. Remember, YA is the output. So this is the whole circuit like this. And YA and YB are the outputs and X are the inputs. So whenever you find an equation, you find this equation as a function of the input X and also the states QA and QB, not the output. Okay. So, and the second input is X, and the third input is basically QB. So DA is equal to QA XOR X XOR QB. And DB is really easy because it has just it's the output of this inverter, and this inverter takes QB here. So DB is basically QB bar. These are basically the 4 equations. Let's check now the correct answer. So yes, YA is QA, YB is QB, DA is QA, QB, XOR, QB, XOR, X, and DB is QB bar. Okay, let's remove now, the ink. Okay, how about the state table? So let's build it. Look, the equations here are a function of all the 4 equations are a function of X, QA, QB. This is in general. Okay, this is basically the input and the present state or the current present state or the current state, whatever you call it. It's just naming, but the meaning is the same. Okay, this is in general. Of course, YA and Q and YB are just a function of QA and QB. Okay, DA and DB are function of all of them in general also. Okay, so when you build the state table, build it as a function of X and the present state. So with this table will be like the following: the input X, the present state or the current state QA and QB. Then based on these, we're gonna get let's do it because the answer will be in that area. So let's do it here. So the input X, present state QA, QB. So the outputs will be, or the functions, or that we build are 4 functions: DA, DB, YA, YB, DA, DB, YA, YB, and also we're gonna build in that table as well the next states for Q and QB. So QA plus QB plus, and again QA plus basically means Q of T plus 1. QA only means the Q of T, QA of T. Okay. So we have here basically you can consider it as 3 inputs or 3 variables. So these 3 inputs or 3 variables are X, QA, QB. Although just one input we have X, Q, and QB are just internal signals, but just to consider them for a moment as just like an input. So there are 3 variables. They take 8 combinations. 0, 0, 0 until 1, 1, 1, 1. So 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay. YA and YB are very easy to deduce. YA is equal to QA and YB is equal to QA. Just copy and paste. So copy this column into that column and that column into that column. Let's do that. So this will be 0, 0, 1, 1, then 0, 0, 1, 1. Then this guy will be 0, 1, 0, 1, 0, 1, 0. Good. DB is QB bar. So take QB column and complement it here. So it will be 1. It's 0, 1, 0, 1. So it will be 1, 0, 1, 0. 1. Sorry. This is basically the correct answer. So 1, 0, 1, 0, 1, 0, 1, 0. And DA is QA, QB, QA, XOR, QB, XOR, X. So it's XOR function. So whenever you have a row, count the number of ones. If it's odd, it's 1. It will be 1. If it's even, it will be 0. So the first row here has 0 number of ones. It's considered an even function. So this will be 0. This has 1, 1. It's an odd number of ones. So this will be 1. It's also 1, 0, 1, 0, 0, 1. Let's check again. Correct, correct, Correct. Okay. Now QA plus and the QB plus. The next state of the next state of each D flip flop. This is determined on D when the edge arrive. So just look at DA and DB. Let's start by QA plus. Just look at DA, okay, and look what happened when the edge arrive, when the clock edge arrive. So when the clock edge arrive and DA is 0, QA plus will be 0. Q of T plus 1 will be 0. Because it's the D flip flop is a transparent D flip flop. Whenever you have in the input will be coupled to the output when the clock arrive, when the edge arrive, either positive or negative, whatever the type is. Then when the A is 1 and the clock arrive, this will be 1. When the clock arrive and the A is 1, also will be 1. So basically copy this column into that column. So it's 0, 1, 1, then 0, 1, 0, 0, 1. And the DB is the same. Also, it's a D flip flop. It copy the input D to the output Q plus, the next state, when the clock arrives. So copy that column now into that column. So it will be 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. That's basically the state table. Okay, so let's omit here that part and check the correct one. Okay, so if we so we have first the XQAQB, the input. This should be separated somehow. It's a typo, so here is an input, so the input should be in a separate column. That's usually what we do. So but anyways, so input and the present state from 0, 0, 0 until 1, 1, 1. So DA is 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, that's right, 0, 0, 1, 0, 0, that's right. DB is 1, 0, 1, 0, that's all right as well. QA and QB, of course, will be correct because it's just like copy and paste. Look, it's a copy and paste. This guy, this column is basically this column, and that column is that column. And finally, YA and YB are basically QA and QB. These two columns in the beginning here will be copied here just exactly the same. Okay, guys, that's basically the state table. Finally, we're going to build the state diagram. So let's omit all of that and try to build it. So to build the state diagram, we should know the number of states. And for each state, we're going to make a circle. Okay? So you have here two flip-flops. Two flip-flops. Each one has a state, right? So you have two states. Two states makes 4 combinations. So you have 4 of these circles. Let's do it here, for example. So a circle, another one, third, a fourth. So each circle represents a state. The state here is basically 2 states together because we call for the whole circuit the one state, which is basically the 2 outputs of the flip-flops together. So the first state, if the 2 outputs of the flip-flops are 0, 0. Second state is 0, 1. Then third state is 1, 0. Fourth state is 1, 1. Again, when I say the state of the circuit is 0, 1, that means there is a 0 here and 1 here. When I say the state of the circuit is 1, 1, that means there is 1 here and also 1 here, and so on. Okay? Now, let's check how these states are transitioning to each other. Okay, based on the input and the current state. Okay. And also, the output. This is basically, as we said, a Moore circuit. So the output Y is only dependent on the state of the circuit. It's not dependent on the input X. That's why we can do it right now. So let's change the color and make the output. Look, we're gonna write the output in the same circle, just underneath the state. So when QA is 0, YA will be 0. When QB is 0, YB will be 0. That's what we have here. Look, 0, 0, we have 0, 0. 0, 0, we have 0, 0. Okay? Now, when QA and QB are 0, 1, look, YA and YB are 0, 1. And 0, 1 here, also 0, 1 here. When QA and QB are 1, 0, YA and YB will be 1, 0. Look, 1, 0, 1, 0, 1, 0, 1, 0. Finally, when QA and QB are 1, 1, yeah, that's so YA and YB will be 1, 1 as well. So finally, 1, 1. Now the transition between states. This is again more circuit. So the transition between states is dependent only on X. So let's check that. And so of course, and the current state, I'm very sorry. It dependent on the X input and the current state. So let's change the color again, for example, to this cyan here. So if we are 0, 0, and the X is 0, the next state will be 0, 1. Good. If we are 0, 1, and the X is 0, we're gonna go to 1, 0. If we are 1, 0, and the X is 0, we're gonna go to 1, 1. Look, I am looking at the current, the input X, the current state, and the corresponding next state. Finally, if the state is 1, 1, I mean the output of the two flip-flops are 1, 1, and the input is 0, then we go to 0, 0. Good. That's really nice. But did we finish? No. Because for the same states, if the input is different, you're gonna have a different, outputs, different next states. I'm sorry. So let's do that as well. So let's change the color again to, for example, green, or that, black. Yeah. So again, when the current state is 0, 0, but the input now is 1, we're gonna go to 1, 1. So look, the current state is 0, 0, but the input is 1, we go to 1, 1. Now, when we are 0, 1, the current state is 0, 1, and the input is 1, we're gonna go to 0, 0. So if you are 0, 1, this is state in here, and the input is 1, we're gonna go to 0, 0. Okay? If the state is 1, 0, and the input is 1, we're gonna go to 0, 1. If the input is 1, 0, which is that case, that state, and the input is 1, we're gonna go to 0, 1. Finally, if the state is 1, it's really difficult. Yeah, 1, 1, and the input is 1, we're gonna go to 1, 0. If we are in 1, 1, and the input is 1, we're gonna go to 1, 0. Perfect. Let's check the correct answer. Here it is. Look, when we are 0, 0, and the input is 0, we go to 0, 1. When you are 0, 1, and the input is 0, we're going to 1, 0. When we are 1, 0, and the input is 0, we go to 1, 1. And when we are 1, 1, and the input is 0, we go to 0, 0. And the rest is the same. Now, we said that the state diagram, is a very intuitive and a very easy way to describe the function of the circuit, and you can basically know its job, right? What is the application, the main target, the main objective of the circuit. So can we guess now what the circuit is really do? That's basically the question. Can we guess the function of the circuit? Yeah. And that's really simple, Just look at it. So look at the sequence, how it goes, and you're gonna know. When we are 0, 0, which is basically 0, as a number, and the input is 0, we go to 0, 1, which is 1. Then again, if we are 0, 1, and the input is 0 again, x is 0, we go to 1, 0, which is 2. And finally, when we are 1, 0, and the input is 0, we went to 1, 1, which is 3. And finally, when we are 1, 1, and the input is still 0, we go back to 0. What is that basically? That's a counter. That's a counter that count up from 0 to 3, then it resets because there is no, you cannot continue because you have only 2 bits. So it resets back to 0, 0. Okay, good. How about if the input is 1? So let's start from 1, 1, not from 0, 0. So when we are 1, 1, and the input is 1, we went to 1, 0. Look, 1, 1, the input is 1, we go to 1, 0. When we are 1, 0, which is, so this is 3, this is 2. When we are 1, 0, when the state is of the flip-flops, or the current state of the flip-flop, or the present state of the flip-flop is 1, 0, and the input is 1, we went to 0, 1. Look, when the current state is 1, 0, the input is 1, we go to 0, 1, which is basically 1. Finally, when we are 0, 1, and the input is 1, we went to 0, 0. Then finally, when we are 0, 0, and the input is 1, we went back to 1, 1. What is this? This is a down counter that count down 3, 2, 1, 0, then reset back to 1, 1, because you cannot go back, you cannot go further than 0 with 2 bits. Okay, so what is that exactly? That's basically an up-down counter. So that's basically, that circuit in here is an up-down counter circuit, digital circuit. Okay. Based on the input X, you can set or configure the circuit to count up or count down. Of course, it's really, one may say, what is the purpose of having just a counter that count from 0 to 3? We should have something bigger, right? Yeah, this is just as, I mean, you can do it for 4 bits or 5 bits or 6 bits, whatever bits you want, whatever the the maximum number that you're gonna reach, you can implement it using the same concept. And if it's already implemented, you can analyze it using the same steps as well. Okay, so that's, guys, our first example on synchronous digital circuit analysis. So in the next recording, we're gonna learn how to design same circuit, and you're gonna see that we go in the opposite way. So here we started by knowing the equation. So we have the circuit, we knew the equations, and based on the equations we get the state table. From the state table we get the state diagram, and we knew the function. Okay, it's a job, it's just a reverse engineering. You started from something that you already have, and based on some analysis you knew what is the function of the circuit. In the next recording we're gonna design. We will start from just a blank idea in your head that you want to implement an up-down counter. So what will be the flow that I'm gonna use to design or reach to exactly the same circuit here? Okay, guys, thank you very much for watching this video, and see you in the next video. Bye-bye.